So picking up where we left off, we are looking at the direct stiffness method as our introduction to the finite element method, something that we can kind of calculate by hand and really see how all the underlying parts or components are being addressed kind of under the hood and in most commercial finite element software programs. We're looking at trusses for a couple of reasons. One, we can look at planar trusses, so they're in 2D. That means we just have fewer degrees of freedom, so it's going to make our matrices smaller. Another reason we're looking at trusses is because a truss in a way is, you can think of it as kind of a meshed 3D structure. So maybe you could imagine this being a triangular plate, which we're splitting up into meshes where we have these black circles acting as nodes, or these joints connecting the various members that span them. And if you recall, there's an overall kind of procedure that this direct stiffness method follows, and that's up here. And what we're doing is looking at how to idealize the structure, how to break it down, and then how to assemble it into a complete structure such that we can solve the problem. Okay, so last class we covered idealizing the structure and disassembling it. If you recall, thinking about idealizing the structure, we kind of know the equation we want to solve. We simply want to solve F equals KU, where F is the force, K is the stiffness, and U is the displacement. And we want to solve that at every node. So we're going to get the reaction forces at every node. Or vice versa, we can apply some known forces at every node and solve for the displacements U at every node. Either way, what we're looking to do is solve the equation F equals KU. Now, F is going to be a system of equations. If you recall over here, F is the components of the forces in the X and Y direction at each node. Similarly, we're going to have displacements in the X and Y direction at each node. And so in order for there to be this 1/6 vector being equated to another 1/6 vector, we need a 6/6 stiffness matrix to connect the forces and the displacements. And this is what's known as the master stiffness matrix, and that's what we did down here. You'll notice that none of these symbols have a bar over them. Everything we're doing up until this point is living in the global coordinate system of the structure. So, for example, that is given by X and Y, which we chose to center at the node 1 in the lower left-hand corner of our really simple truss, this 3-member, 3-joint truss. We set the coordinate system at the lower left-hand side of that, and everything we're trying to solve, F equals KU, we're trying to solve for that system of equations in these global coordinates. Now, we can't do that yet. We are unable to solve for these things because we don't know what K is. So our job now in steps 2 and 3 of breaking down the structure and reassembling the structure is to solve for what the stiffness matrix K is. Okay. So as I scroll down a little bit, this breakdown or disassembly is really about taking our structure right over here to the left and splitting it up into 3 individual components. And so in order to do that, we essentially split up all of these nodes. It's almost as if we're pretending now that there's 1, 2, 3, 4, 5, 6 nodes that don't even know about each other's existence. We're kind of just saying, okay, I have 3 bars. Each bar has 2 nodes, And I'm going to look at each bar individually. And I can do that by, I can say, well, I'm going to use the simplest way to approximate what's connecting these two nodes. And I'm going to say it's just a spring. And that spring has an effective or equivalent spring stiffness. K is equal to EA over L. Okay, so now you're seeing that what we've done is we've introduced these local coordinates. So each member of the structure has its own coordinate system that it lives in. And the coordinate system is defined such that the X bar direction runs in the parallel to the member of the structure, and the Y bar direction is orthogonal to that. And we're going to have to keep track of all these different coordinate systems. We're going to have an X bar for member 1, and a Y bar for member 1, an X bar for member 2, same, and so on and so forth for all these local coordinate systems. And the big result out of what we did last class was to arrive at the local stiffness matrix for what are called these two node members, these two node bars that we're using. So the simplest possible way to model the connection between these nodes is to treat them as linear springs or two node bars, where they can only have resistance to stretching axially, and there's no bending or torsional ability. We're going to ignore all those physics for right now. We're just going to look at kind of bars connected at nodes that can stretch or compress. And each of these bars has a stiffness matrix that is given by EA over L for the given element times this matrix of ones and negative ones and zeros. And this is our way of essentially connecting the forces for each node to the displacements for each node based on the stretching or compression EA over L of each member. So what we have done so far is we've gotten the local stiffness matrix. Now, what's great about this is that this local stiffness matrix is applicable for every member in our structure. So we have this kind of K bar E. So we could solve F bar, which I guess I should write that. I don't think that's here. You know, we can solve F bar E equals K bar E times U bar E. We can solve these equations locally. It's just the spring equation, F equals KU, or F equals KX for typical springs. And so we have this in local coordinates. Our next step is to transform this stiffness matrix for each member from local coordinates to global coordinates. Once we have the stiffness matrix for each member in global coordinates, we can add them one by one to the big master stiffness matrix, the one that's in purple above the text breakdown. So that's the goal. That's the procedure that we're trying to follow. We've successfully gotten the stiffness matrix in local coordinates for a two-node bar. We have to transform that into one for global coordinates, and then we have to add that into the global stiffness matrix. Okay. So this is, in order to do that, we really have to look at some transformations. Just like we've done in the past, we have something in one coordinate system. We'd like to convert it to a second coordinate system. And that second coordinate system here is going to be that second coordinate system is going to be the one defined at the beginning, where the x and y are taking place at the lower left-hand node. Okay, so let's look at a general member at some arbitrary angle relative to the global coordinate system. So let's draw this. So I'm going to say I have a member here. Our global coordinate system is defined by x and y. And what we can recall that our local coordinate system x bar and y bar exists such that x bar is parallel to the long axis of the bar, and we can say that in between these two, I'm going to make that a little bit easier to see. Sorry about that. So we can note that this is our ith node. This is our j node. There's going to be an angle theta from our global coordinate system to our local coordinate system. And correspondingly, we know that we expect there to be some displacements in our local coordinate system, which we would denote u bar xi. These can occur at both nodes. So this would be u bar yj, and this would be u bar xj. And what we really want is we want to know how these displacements u bar at each node relates to the displacements u at each node, depending on the orientation of this member. So what we really want are to calculate, the displacements uxj and uyj. And similarly, uxi and uyi, we want to know how to relate the displacements in our local coordinate system to the displacements in our global coordinate system. And this is just a typical stress transformation, matrix transformation. Any of the transformation work we've done in the past directly applies to what we're doing here. And so you can kind of start to see how you can split up these components just by trigonometry, relating the displacements in our local coordinate system to the displacements in our global coordinate system. So let's write that out. So we will say that we'll go up here. So we'll say that the displacements in our local coordinate system, ux bar I, will be equal to uxi times the cosine of theta plus uyi times the sine of theta. This is just a typical transformation of kind of relating the new lengths, the projection of our displacement vector u, the red u bar xi, into the x and y components. So we're just decomposing our red vector uxi, and we're going to do that for all of them. And so we can keep going. U bar yi in this case, this will be negative uxi sine theta plus uyi cos theta and then again we can just repeat this for xj and yj. So just to recall, our angle here, theta, is the angle between x bar and x. I'm going to take a little shortcut here. So, oops. I'm going to do a little shorthand notation. So, theta is between x bar and x. And I'm going to do a little shorthand notation, which I'm going to say let us write cosine theta as little c, and let us write sine theta as little s. This is going to seem kind of pointless for the moment, but in a minute when we start to put all this together, it makes writing out the larger matrix a lot simpler. Okay, so we can take these equations and write them in matrix form. And so we would say that that u bar xi U bar yi, U bar xj, and U bar yj. And these are all for the individual elements. So I'm going to put a superscript E on top of that just to remind us that we're still working for our displacements on a given individual element. So these will be equal to our all of our trigonometric relations. So we're going to have cosine, sine, negative sine, cosine. You're going to remember this is looking like a typical rotation matrix that we used earlier in the semester to do stress transformations. You're still seeing this same transformation approach applying over and over again, kind of bringing us back to some of the important concepts that we learned in linear algebra, just understanding how to relate matrices between different coordinate systems. And that's all we're doing here, is we're just taking for this case, the displacements in one coordinate system and mapping them to another. And in a moment, we're going to do the same thing for the forces. So this is going to be a 4x4 matrix because it's a 1x4 vector on each side. So it's going to be 0, 0, 0, 0, 0, 0, 0, 0. And then again, we're going to repeat C cosine, sine, negative sine, cosine. And these are going to relate to our displacements. So I can and this will give us u x I u y. Oh, whoa, that's not right. And again, this is true for a given element. Same thing for this transformation matrix that's multiplying them. Okay, so what we have here is a mapping of our displacements in our local coordinate system to the displacements in our global coordinate system by this transformation matrix. This looks a little bit like the transformation matrix you used before. Typically, those were 2 by 2. If you're just transposing, say, kind of one part of a vector or one component of stress. But here we end up with a 4 by 4 transformation matrix. So we'll call this the elemental transformation matrix. We'll give it a the symbol T with an E above it to denote that it's a transformation for a given element. Okay. It's square and orthogonal. This is not generally the case if you have more complicated elements involving connecting to particular structures. It doesn't have to be square. There's a lot more. This can become a lot more complicated as your elements become more complicated. But for this really simple 2-node bar, this just looks like kind of your typical transformation matrix, augmented so that it's got some zeros to the left and right and below it. Sorry, to the right and below it, and then another transformation matrix in the bottom right. This is not crucial to your understanding of this material. This is not crucial to understanding how these transformations will be applied. But you're going to notice in a second that when we solve for the forces, we are going to have a different set of equations where we're going to have our global coordinate system appearing on the left-hand side of the equation and our transformation matrix multiplying the local components on the right hand side. This has to do with some kind of subtle properties of geometry and transformations. In particular, if you're interested, this is what's referred to as a covariant transformation. And in the case of force transformations, we're going to be dealing with contravariant transformations. If this doesn't make any sense or these words are unfamiliar to you, that's fine. If you're curious about why in particular they appear the way they do, this will give you some things to go look up. Basically, different vectors transform in different ways. There's a lot of kind of complicated concepts underlying this. For right now, I just want you to know that these things are going to forces and displacements are going to transform in different ways. Displacements transform covariantly, so it's going to look like local coordinate system on the left, transformation times local global coordinate system. Forces transform contravariantly, so all that's going to be flipped. So I'll show you what I mean. Okay, so let's look at, so this was our displacement transformation. And let's do this again, but let's do this for our forces. So I'm going to take the same drawing here. Except I'm going to go in here and we're going to erase all of these. And what I'm going to do is going to write down how these same properties, but for our forces. So, for example, the forces in our global coordinate system will be Fxi, Fyi at the ith node, and then we're going to have F bar xi and F bar yi, and then similarly we'll have fxj, fyj, and then these transformations relative to their local coordinate system, f bar xj and f bar yj. Now, the node forces transform differently. This is what I was just saying a moment ago. The node forces transform such like this. The node forces transform such that f of x I will be equal to, now that's in our global coordinate system, will be equal to f xi locally times the cosine of theta minus f yi local times the sine of theta. Now we can do all of these. So we can write down, for example, FYI It's going to look nearly identical to what we just did before. Except you're going to notice that our signs are flipped. So what I want to point your attention to is here. So above, this one was positive, and now it's appearing negative. And as we go down to where we're going to see that our force in the y direction will have a positive component, F xi times the sine of theta, and F yi times the cosine of theta. So the negative sign switched locations. This will make more sense in just 1 second. So we can keep doing this. So we can write, oops, let's do that in the right color. We can write F xj And so we end up with a very similar matrix equation, except everything's flipped. On the, like I said, forces and displacements transform in opposite ways. And what that means is that what you're seeing here is that we're writing the global forces on the left-hand side, transformation times the local forces. What we're going to end up with, since everything is flipped, and you can kind of get the sense of by looking at these equations now, what we're going to end up with is a transformation matrix, TE, that is the transpose of what we currently have. So we can, I can see if I can. So let's go in here. So what we're really doing is we have to take, we're kind of switching here. So we're switching such that, oops, such that everything in red, which is in our local system, is going to appear on the right-hand side of the equation. And everything in purple, which is our global coordinate system, is going to appear on the left-hand side of this equation. And in order for that to work, we have to look at the transpose of our transformation matrix. If you don't see this, if it's not obvious, that's fine. But if you just go into the equations that we wrote down on the left-hand side there, then what we'll find is that the negative signs for the for sine and cos for the sine terms are going to flip location. So we're going to end up with this term being positive, this term being positive, and our negative signs appearing here and here. And then I can just go through and write out all the forces here. So this is going to be F xi, F yi, F xj, F yj, and then, oops, that's not right, F bar, xi, F bar yi, and the same for xj and yj. And just for the sake of, if you're interested in doing a deeper dive here, this is what's known as a contravariant transformation. Forces and displacements transform in different ways. There's a lot of really subtle, interesting things to how to think about how different vectors and different tensors transform. But that's for another class. That's for further down the road. But right now, just knowing displacements transform one way, forces transform a second way, and those two ways are kind of orthogonal to each other. That'll be enough for us to calculate what we need here, which is we need to calculate the member stiffness matrix in global coordinates. So just to recall, we have the member stiffness matrix in local coordinates. We're trying to calculate what the member stiffness is in global coordinates. In order to do that, we're going to need to basically say, hey, this member is oriented in this angle theta relative to the global coordinate system. And that's what we're doing here. We finally we introduced this angular measurement between the local and global coordinate system such that now we can transform all of our equations from local coordinates to global coordinates. Okay, so let's see how we do this. So we were looking for the global member stiffness matrix. Global meaning global coordinate system, member meaning it's just going to be the stiffness matrix for a given member, not for the whole structure. That's the master stiffness matrix. And so how we're going to get this is we're going to say, well, okay, look, we know that from above we can write down in local coordinates that F bar is equal to the local stiffness matrix in for the member times the displacements for that member. The equation we'd like to solve is not that one. The equation we'd like to solve our problem is the same one, but we'd like to be able to solve F equals KU for each member, but in the global coordinate system. So now we have almost everything, right? We have, let's see here, KE is this thing. So I'm going to copy that. Never mind. I'll just write it down here. Okay. So we have these relations for U bar and F bar. So U bar is straightforward. So we're trying to get to the equation in purple. We have the equation in red. So for instance, we know that U bar, so let's go back up to here. So this equation states that U bar, for the element is equal to this transformation matrix, TE, times U for the element. So U bar E is equal to the transformation of this element times U in the global coordinate system. Okay, so we can replace U bar here. We know that U bar E is equal to our transformation of matrix of that element times UE. And so now we can take F bar E is equal to K bar E times the transformation matrix times the global displacements. So we've got one part of this in global coordinates. We've got the displacements in global coordinates now. Now what we'd like to be able to do is get the forces in our global coordinates. So we currently have F bar. We don't have an equation for F bar, but if you go back up here, what we have is, oops, I was misleading here. Sorry, everyone. This is not TE. This is TE transpose. This is FE. And this is F bar E. So we have an equation here that says FE is equal to the transpose of the transformation matrix times F bar. Now down here, we have F bar. So in order to get to F, if we multiply both sides of the equation, in particular here, we're going to left multiply both sides of the equation by the transpose of the transformation matrix, then we'll have on the left-hand side our force vector in global coordinates. And let's see what happens on the right-hand side. So we can come back down to here. We can take this equation. Let me do this. We're going to left multiply by the transpose of the transformation matrix, because that'll make the left-hand side equal to F, which is what we want. So we can say T E transpose times F bar E equals TE transpose times what we have left over here. So this is K bar E times the transformation matrix times UE. And now recall that the left-hand side of this equation is equal to the force vector in our global coordinate system. And so now we have what we want. So now we have FE is equal to something times UE. And we know that from up here, that something has to be our stiffness matrix for the member in global coordinates. So this thing here is equal to KE. So this is really important. This allows us by knowing the stiffness matrix in local coordinates and knowing how to transform our displacement vectors and our force vectors, we can write out the stiffness matrix for the member in global coordinates. Okay, so that means that KE is equal to the transformation matrix transpose times the stiffness matrix in its local coordinate system, which we already calculated, times the transformation matrix. This is really important. You could have just kind of guessed this, right? That sounds crazy, but if you think about it, every time we transform something, so we're transforming some matrix, if you go back to your notes thinking about stress transformation, you end up with an equation that says the stress in the new coordinate system is equal to the rotation matrix transpose times the stress in the old coordinate system times the rotation matrix. It's the same equation. The linear algebra here is not changing. Everything that we're doing right now is stuff that we did before when we were looking at eigenvalue problems and stress transformations, and you end up with an equation that has the same form. The difference is, you know, we could have guessed maybe the form of this equation to figure out what KE is. Well, I got to find my KE bar and then transform it. So I'm going to have a something transpose KE bar something. And the thing is calculating what that transformation matrix is what would take a little bit of work. This calculation is not too bad. I did it in Mathematica. I can try to briefly share my screen on that. I worry that I'm going to mess up this video or this class if I do this. But let's see if I can get it to work. So let me see if I can share. Here we go. Okay. Hopefully now you can see Mathematica on your screen. And so what I've done, if you can see this, is I've entered the local member stiffness matrix. I left off this prefactor, EA over L, which will multiply this matrix. That's just to prevent Mathematica from distributing it through. I want you to be able to write this down and see how it looks in terms of ones and zeros and cosines and sines. So this is just KE bar. This is what we have written down. We did last class, deriving the local stiffness matrix. And imagine that there's a prefactor EA over L multiplying this term. So the displacement transformation matrix is what we found by looking at how to relate displacements in the local coordinate system to the global coordinate system. And we end up with this kind of these two rotation matrices here, cosine, sine, negative sine, cosine appearing in the top left and bottom right of this matrix. So this is our displacement transformation matrix. We know that the force transformation matrix is simply the transpose of the displacement transformation matrix. So I write down transpose of TE, and I get the matrix that we just wrote down a moment ago. Now to calculate what we want, which is this global member stiffness matrix, so that KE, we need to take the transpose of the transformation matrix times KE bar times the transformation matrix. And so doing that here, and again, that term EA over L will be outside of this parentheses. I'm leaving it out for right now. Doing that here, we end up with this complicated mix of cosine squareds and cosine times sine. Now you can see why I chose to abbreviate cosine and sine as C and S, just because this matrix becomes a lot less readable in that form. But this is what we're going to write down when I go back to the iPad and take these notes down. But this is how we're going to get to this equation for the global stiffness matrix of a two-node bar. Just calculating TE, TE transpose, and then multiplying them together with our stiffness matrix of the bar in local coordinates. All right, let's go back and pick up our notes. Okay, so great. So now we can write this out instead of in this matrix notation. We can write this out explicitly such that KE is equal to the member stiffness, EA over L. And then I'm just going to write out what I just showed you in Mathematica. So it's going to be cosine squared, sine cosine, negative cosine squared, negative sine cosine, sine squared, negative sine cosine, negative sine squared, and now again, it's going to be cosine squared here, sine squared here, and now you're going to flip the sign. So it's sine cosine and then sine cosine. I guess I can delete that one. So this one here is symmetric. So you can kind of write out these entries on your own. You can, I'm going to note that this is our member stiffness matrix. In global coordinates. And just quickly, you should be able to check to see that the member stiffness matrix in global coordinates will recover the local stiffness matrix when we have a flat bar so that the angle theta is 0. They should be the same, right? It should be the same as 1, 0, negative 1, 0, 0, 0, 0, 0, and so on. And you can see that if I put in theta is equal to 0, then you're going to get 1, negative 1, 1, and then this one here would be negative 1, and then everything else would be 0, because anything you have a sign appearing in is going to go away. So this quickly, just by putting in theta is equal to 0, which corresponds to the flat bar, which is how we derive the stiffness equation up here for this flat bar. We end up recovering what we expected, which is this stiffness matrix. Oops. Oh, okay. Okay. All right, so that's a lot of work. But now we have the ability to calculate the stiffness of each member in the global coordinate system. Once we do that, our next step is to calculate it for each member and then put that matrix into the master stiffness matrix. Before we do that, let's do a little practice. So let's go back to our truss. So let me bring this thing down here. And let me give you some properties here. Let me say that we'll say that EA for member 1 is equal to 100. EA for member 2 is equal to 50. And just to make our math easier, I'm going to give you an EA that's going to be strange looking, but it's going to help simplify. Take it as 200 root 2. Just by geometry, we can note that the length of, we'll take the length of the first member as 10, the length of the second member as 10, and then just from geometry, we know that the length of the third member must be 10 root 2. And we can take our angles. Theta is 0 for the first member. Theta is 90 for the second member. And theta is 45 for the third member. And now note that in each case, we're going to take I and J as the global joints. So for instance, the joints connecting the joints that are applicable to member 1, so looking at this one as member 1, are 1 and 2. So this one has joints 1 and 2. So that means when we think about keeping track of I and J, we should be using I as 1, J as 2. Now in the next case, if we look at member 2 has, let's not do that. Member 2 has 2 and 3. So we can write 2 and 3 over here. So in this case, I would be 2, J would be 3. And finally, for the third member, it's being connected by joints 1 and 3. This is going to become important when we go to reassemble this master stiffness matrix, the global master stiffness matrix that's going to allow us to solve for the displacements of our truss. What I'd like you to do for a minute is to see if you can use this member stiffness matrix in global coordinates to write out the force displacement relationship for each member. So you should be able to write something like this. So for member 1, we're going to have that the force in global coordinates now, x1. So note, I'm being really kind of careful here to make sure that we're calling everything correctly. Let me try this again. So member 1 is connected by joints 1 and 2. Oops. So just to remember what our notation is, the number in parentheses is what member are we talking about, and the subscript below x and y is what joint are we talking about? What degree of freedom are we talking about? And so we should be able to relate F, this thing, to my displacements. So again, we're going to be thinking about ux1 for member 1, uy1 for member 1, and then ux2 again for member 1, uy2 for member 1. Okay, this one's pretty simple, right? This one is quite trivial. So EA over L all of this for member 1 is equal to 100 divided by 10. So that's just 10. Let me make some room here. And then it should be pretty trivial since this one corresponds to the case where theta is equal to 0. So if theta is equal to 0, we should recover our simple stiffness matrix that we found before, where, for instance, we have 1, 0, -1. And then this term equals 10. So we now have the exact global stiffness relationship between force and displacement of member 1. It's going to be 10 times the matrix of 1s and -1s and 0s. And that matrix can be found by just taking this matrix and putting in 0 for theta in all those terms there. I'm going to write all this stuff out so you can see it, but I would encourage you to take some time and confirm the calculations that I'm doing here.
Professor?
Yes.
The three element shouldn't be 1.
3 element. Oh, yeah, it should be 1. Thank you. Don't know how that happened. Thank you. Perfect. Okay. The next one is pretty simple too. So I would encourage you to try these out on your own. The next one's pretty simple too. And I'm gonna actually copy this one. That's probably a bad idea because I have to write out all the different things here. So, okay, never mind. So let's just write this one out. So for member 2, now recalling that member 2 has joints 2 and 3. So we're going to again have so it's going to be fx2. This is for member 2. fy2. And then nodes 3 for the second part. This one's not too bad either because we're going to have 50 divided by 10, which is 5. And you could probably guess the entrance to this matrix if we're now flipping from this is member 2. So instead of being horizontal, we're vertical. So we're kind of shifting all of our sines and cosines by 90 degrees, right? Because we went from 0 degrees here to 90 degrees here. And that basically has the effect of taking everything in the matrix to the left, that's a 1, and turning it into a 0. And it's essentially going to make all of the sine squared terms equal to either 1 or -1. So this matrix is going to look like this. And again, if it's not clear where this is coming from, just go back to the KE matrix and put in theta is equal to 90. So this one's going to be 0, 0, 0, 0, 0, 1, 0, -1, 0, 0, 0, 0, 0, -1, 0, 1. And this will relate to all the displacements in X and Y for the nodes 2 and 3. The last one is not quite as simple, but again, using that the global stiffness matrix KE and putting in 45 degrees, you can work it out. And I'm just kind of writing this all out. I know it's a bit tedious, but I think it can be helpful to see, okay, these are the individual equations for how force and displacement responds for all of the different components of my structure. And you can kind of clearly see that really what I'm doing is I'm just treating member 1 as if it's completely unrelated to member 2. And I'm treating member 2 as if it's completely unrelated to member 3. And I'm just saying, how does the forces acting on member 2 cause displacements on member 2? And it causes displacements through this stiffness matrix. Okay. So member 3. And so finally, apologies for the tediousness of this. Again, remember 3, so I have 3 in parentheses, and remember 3 connects joints 1 and 3, so it's going to be fx1, fy1, and then fx3, fy3, this one we chose this weird EA to have the root 2 in there just because the triangular length has a root 2 in, so it makes our math easier. So we're going to do 200 times root 2 over 10 times root 2, so that'll just be 20. And then we can fill in the rest of our matrix here. This one is not intuitive, or at least not to me. So, you really have to kind of go in to the equation for KE and put in theta is equal to 45 and confirm that you get something that looks like a bunch of 1/2s everywhere. So 1/2, 1/2, -1/2, -1/2. And then following on through. And this again is ux1, uy1, ux3, uy3. And now we have all the force displacement responses for the 3 members of our truss. These are not part of the structure in the moment. The way we formulated this is really just saying how do forces and displacements respond for each of these individual members. But what I want you to tell me is not how the force and displacement response is relative to their local coordinate systems. I want you to tell me relative to this arbitrary global coordinate system. That it's only arbitrary because it's relevant to the overall structure and how the structure is oriented. But if up until this point, these members of the structure, they're not. It's not clear how they're connected, and that's what this last part is going to accomplish. Is what we're the last step here. This is still really part of just the breakdown. So if you go back up to where we started, we said we first need to idealize the structure and then break it down or disassemble it. So really all we've done now is kind of finish the breakdown part of it. We broke it down, figured out how things work in the local coordinate system, mapped it to the global coordinate system. Now that we have everything calculated for the global coordinate system, our goal is going to be to reassemble each of these individual elements into a structure, such that when I push down on this node, both this part and this part feel it. That's the assembly section, and that's what we're going to cover next class. So this is a pretty good place to kind of stop, because the next bit of work takes some time to do correctly. And so let's talk about what questions you have on what we covered today. Nothing? Come on, there's gotta be some questions.
I have a question on how you, how do you decide which node is I and which one is J? Because for example, member 3, at first I thought, okay, I is gonna be 3, and then J is gonna be 1. So how do you decide that it's the other way around? You know what I mean?
Yes, I see what you're saying. So I took.
Is it because of the direction of the axis, of the x-axis?
I didn't say that node 1 for member 3 is the same as node 1 for member 1, because those are the same nodes. So what I mean by that is member 3 I'm looking at as if it's like this. Let me draw this. Where it is 1, 3, and then I looked at this one as though it's 2, 3, and I looked at this last one. Let's see if I can do this such that it's 1, 2. And so what I tried to do was to try to keep my numbering of the nodes to be the same as the numbering for the structure. So this one is the same node as this one, and so they have the same number.
Mm-hmm.
Does that make sense? Does that answer?
Yeah, but what I mean is, no, the thing is, why member 3, your I node is that one? Because I thought that we were going like anti-clockwise, or I don't know how that's said in English.
Mm-hmm.
So from 1 to 2, then to 2 to 3, and then for member 3, we were going from node 3 to node 1. So for me, node I would be the third one, and node
Yep.
J will be the first one. So at first I wrote it like that, and then I saw what you were writing, and you put it the other way around. So is it arbitrary or
It's
like
not
or
arbitrary.
something? Or
It's not arbitrary. My recommendation would be to make it so that whatever node. So for instance, here, this node. Is the same physical node as this node. And so I made it such that the numbering is the same. And if you go back to up here, we know that.
So is it for both of them?
Yeah.
Is this the same one?
I had the same doubt. It's maybe because you define theta as the angle between x and I had the same doubt, and I think that it's because we define theta in that way. Otherwise, it had to be 5. Theta has to be 45 plus 180.
Okay. So wait, are you referring to how we?
Yeah, I mean that we have to go from 1 to 3 because we define theta as the angle between the beam 1 and 3.
Right.
So maybe is it because the direction of the x-axis of that member? Because the local x-axis for member 3 is going from 1 to 3, so that's why I is 1 and J is 3. Or
Yes, I think that's right. I think we're saying the same.
Okay.
Yeah. I think that's right.
Okay.
Based on how these local coordinates are drawn, how the angle is defined between x bar and x. So this one here, x and x bar would have 0 angle. Oops.
Yeah.
For member 1, and it would be 90 for member 2, and it would be 45 for member 3. And so I think that's right. I guess I never thought of it this way. I always thought of it as saying, these nodes are the same in physical space. Oops, I can't see that at all. Node 2 is the same as this node here. And so by labeling them the same, I'm really saying, what I really like to do is to say, there's some condition, for instance, on the displacement of node 2 for member 1, such that the displacement of node 2 for member 1 has to be equal to the displacement for node 2 of member 2. Because those two nodes, well, really are just one node. They're the same. Node 2 is the same, and we can connect them, and that's what we're going to do in the next class, is basically say, okay, I know that member 1 and member 2 share a connection at node 2, and so I'm going to take whatever I have written for node 2 and make sure that it's equal to whatever I have written for node 2 and this one. So for instance, what we're going to do next class is we're going to say, well, we know that the displacements of node 2 and x and y for member 1 have to be equal to the displacements of node 2 for member 2. And so on and so forth. We do the same thing for node 3 and for node 1. We're going to assemble the structure, we're going to basically say the displacements at this point have to be the same as the displacements at this point for this member. And that's kind of how we tell, through all this matrix algebra, we kind of instruct how these components form a structure. It's by assigning equality between the nodes. And so this labeling, for me, I think whoever jumped in and made this remark about the definition of the angle is correct. I've always thought of it the other way, which is just to say, I want my nodes to be labeled in such a way that even though member 3 and member 1 are kind of arbitrary, they're going to share node 1. And so I'm going to call node 1 on member 1 the same as node 1 on member 3. I think both of those statements are equal, although I hadn't thought about the question about clockwise or counterclockwise, anti-clockwise for labeling them before. But I've always thought of it as just kind of how do I make sure that I'm labeling things the same, so that way when I want to assemble these components into a structure, I can just say, oh, hey, the displacements at node 1 for member 1 have to be the same as the displacements for node 1 of member 3. I don't know if that's a long, convoluted answer, but hopefully that helps.
No, but that makes sense. Okay. Yeah. Thanks.
Great. Other questions?
I have a question about the stiffness matrix local. My question is, we started with the model of the linear spring. Just for the sake of curiosity, is this the ultimate model? Or it's like the first one to start with, or it's the best one to describe trusses?
No, this one is not. This one, I guess I should say that this one is adequate to describe trusses, because trusses are typically pin connected, so that there's actually no bending of the elements between the pins. And so in that case, you're basically saying, well, if they're pin connected, there's not going to be any resistance to rotation of those elements. And so the only thing that's going to happen is that there's going to be compression of tension. And if you force it to be in the plane, then there's really no possibility for kind of torsion or out of plane deformation. And so in that case, for a truss, the axial rigidity is the only thing that really matters. Now, the reason we pick a truss, and the reason we pick a truss is because the point of this is not really to have a excellent code for calculating truss deformations. It's really to show you how you do this process of idealizing, breaking things down, and assembling. It just so happens that we picked a structure so that way you can make the simplest possible direct stiffness method or finite element method, because it's really just got one part of physics, just compression or stretching. And everything else is
yes,
zero.
because I was wondering about this local stiffness matrix and thinking, is this the only stiffness matrix that we can define?
Oh gosh, no. That's where so that's a great question. That's where the mechanics comes in. Like, that's where you say, okay, I am interested in stretching, bending, torsion, and now you could get even more creative. You could be saying, I'm interested in how these things work under gravity. I'm interested in electromagnetic interactions. Your stiffness matrix will just grow and grow and grow and grow. Because what happens is, for each level of physics, so for instance, right now we just need to care about relating force to displacement. What we'll see in a couple of days' time is we will kind of go through the next level of difficulty element, which is a beam element. And a beam element has displacements and moments. And so you end up with another 4x4 matrix if you have only bending appearing. Now, if you want to do something more complicated and say, I want to look at a structure where there's stretching and bending, these are typically called frames. So any frame, like your desk, would be a frame. Your frame, the legs of your frame on your desk. Imagine a desk that's kind of spanning, here to here. Your legs are under axial compression. Now, the member connecting them, the top of your desk, the stuff that you work on, could flex and could bend. And that flexion could cause maybe even bending of the legs of the table. And so that frame is basically the simplest structure that includes axial and bending. Now, axial has a stiffness matrix that's 4x4. Bending has a stiffness matrix that's 4x4, but a couple of the components are similar. what you end up with for a frame element is, I think it's a 6x6 matrix. Yeah.
In which I will include on the right, I would include the angles, and on the left, the moments. Is that right?
Correct. Exactly.
Okay, so you answered my question.
Yeah, and so you can keep growing and building up, and that's conceptually how you would do it. Now, what we'll find and what we'll do at the very end of this class is to show you that kind of calculating the stiffness matrix by hand gets really complicated. And they're going back to what we did for the first online lecture, where we looked at variational principles. It turns out that these same variational principles, principle of virtual work, minimal potential energy, calculating the variation of the total potential energy, it turns out that that method is really useful for calculating the stiffness matrix, for basically deriving the stiffness matrix mathematically. So we're going to come back to that full circle. We won't implement that code. We are going to implement this code. But the work on the, as you add more complicated physics, calculating the stiffness matrix, as you will see, gets just really, really tedious and complicated. And so there's other ways to do it that build on those energy methods that we talked about before. But yeah, this is just the simplest thing, and it works for trusses because trusses are pin connected, and there's only axial rigidity, so it ends up being doing a good job of modeling truss behavior.
Thank you.
Okay, so this is all I have for you today. I will upload this video. I will send you this PDF. Again, next class, we're going to continue. We're only really done with step 2, which is the breakdown. And now we're ready to do the assembly of this, of these components into a structure. And once we've assembled it, at that point, we actually can apply the boundary conditions and solve a toy problem for this.